Okay, so welcome back. This is part 4 in our series, Control Systems Made Easy. I encourage you to look at the previous videos in the series where we talk about conceptually how do control systems work and give you an intuitive understanding rather than what you see most university professors give you, which is pages and pages of complicated differential equations. In this channel and on these videos, what we try and do is give you a conceptual understanding so you understand intuitively what's going on. So then hopefully once you understand intuitively what's going on, you can make your own equations and the differential equations become, oh yeah, that's obvious. So I encourage you to take a look at the previous videos and other videos on this channel. And if you like any of these videos, please hit the like button, subscribe, hit the bell notifications, and most of all, please let others know that we're here so we get some views. Really appreciate it. Now, what we're going to do in this video is we are going to take the next step in our series, and we are going to design and build a very simple analog circuit on the bench that shows you the basics of a control system. Now, in the previous videos, again, we talked about the concepts and the components of a control system. And in the previous video, we developed this software application that basically simulates a very simple control system. And throughout these videos, we have used an intuitive model of a control system, which is you driving a motorcycle. And this simulator here simulates you driving a motorcycle. We'll start up the simulator and you can see we are plotting the engine speed and the throttle position controlled by you. This slider bar, we slam this throttle up to maximum, and you can see in blue is the throttle position and in red is the actual speed of the motorcycle. And you can see we've got 10, 15, 20 seconds, and we compared this and we used this plot of actual motorcycle speed for a Honda CB500F motorcycle, and we use that as a model for our simulator to see how we could match this speed. And you can see over about 35 seconds it gets up to over 110 miles an hour. And here is our simulator, and you can see after about 30 seconds it's up to around, here we've got 100, 120, around 110 miles an hour. And what we're going to do in this video is we're going to take the next step. Now, it's nice to have a conceptual understanding and build a simulator, but at the end of the day, we want to have an actual electronic control circuit that actually acts like an actual control system. So we're going to take a look at that in this video. And the way we're going to do that is we're going to start out with a free piece of software, an electronic simulator software called LT Spice. And I've done a bunch of videos on LT Spice showing you how it works. I did a series, LT Spice Beginner to Expert. Again, it's a free piece of software that allows you to understand electronics, build up some circuits and simulate them. In this video, we're going to make this simple model that you see here of a few simple electronic components that we can build on the bench. And we can modify the values, the component values, and see how it affects our simulation. The results of the simulation, and again, we're just using a few resistors. You can see here we've got an integrated circuit with a couple op amps that you can get for a few pennies, and a voltage source. And with all of that, we've got a very simple model of a control system, which is you operating a motorcycle. And the results you can see right here. I've got 3 charts here. The top one is a simulation of the speed of your motorcycle. And you can see it starts out at 0 and it slowly goes up to, in this case, 55 or 60 miles an hour. And then you can see the throttle position. So what we did is we slammed the throttle to fully open, which is at a 1 here. And it stays there for half a second, and then it drops down to almost 0 as the speed gets up to where we want it to be. And here is the error, the difference between the desired speed and the actual speed. And you can see there's a big error in the beginning, and as the motorcycle accelerates, the error drops until it gets down to be almost nothing when you're up to the desired speed. And that is basically the simulation of this very simple circuit. And what we can do, once we've got the simulation, we've got all the values figured out, we can go to the bench and we can, use a few components and wire them up and make a actual control system. So what we're going to do in this video is we're going to look at this, see where did this come from and how can we put this on the bench, and then look at the next steps, which is taking this very simple conceptual model and turning it into a real control system that actually will work. So let's take a look at this. And as you can see, again, we're in LT Spice, and we've got this in 3 separate blocks. And we talked about these in the previous videos. We've got on the right here, we are modeling the machine, which is the motorcycle. And as we said before, it takes a value in as you twist the throttle on the handlebar. It takes that throttle position in as input, and the output is the actual speed of the motorcycle, right? It's going up to 60 or 120 miles an hour. So it's got an input and the output, and it also has an output where it gives the present speed. It feeds that back. This is a feedback circuit. It feeds that back to you as a speedometer reading. So you look at the speedometer, and this block here is basically your brain. It says, okay, it looks at the speedometer and says, here's the actual speed coming in, and this voltage here is the reference value or the reference speed. So for example, if this actual speed is 0 on the speedometer, and this reference says, oh, I want to be 60 miles an hour, this is basically a differential amplifier, which takes the difference between the actual speed and the reference speed or the desired speed and comes out with an error, which is the difference between what speed you want it to be and what's the actual speed. And as we talked before, it takes that error, and since the machine, the motorcycle, doesn't understand 60 miles an hour, all it understands is a throttle position, either fully open or fully closed. So we can feed it through this block here, which can convert this error signal, 0 to 60 or 0 to 120 miles an hour or whatever, and convert that from a 0 to 1 throttle position. And then it feeds it into the machine, and the machine responds. So those are the basic building blocks of our model. Again, this model is going to be a very simplified version. It's not going to be something that we can actually use as a controller. That will be the next step, where we can say, okay, here's the conceptual idea. What are we going to actually use? What are the signals going to be actually, so that we can build an actual control system? So let's start at the right here. As we mentioned in the previous videos, the most important thing is the machine that you're going to control. A lot of people focus on the controller, but really, you need to understand the machine you're going to control before you build a controller. So what we've done here is we have modeled the machine by a simple RC network. Now, why are we using a simple RC network? Well, as you can see from the actual test data from this Honda motorcycle, the speed versus time looks like charging of a capacitor on an RC network, right? It starts out at 0, and in an RC filter, you apply a DC, so you apply the 0 to 1 control signal, and what it does is it charges up the capacitor, in this case over about 35 seconds. But you can see that it kind of sort of looks like an RC filter. So the real simple version, the simple model of this, is a basic RC filter. Now, the devil is in the details, as they say. It depends on, how long it takes for this thing to speed up and what's the actual values. But here you can see we got a very, very simplified version of a machine. Now, the limits of this circuit are that actually the speed in a real machine is going to be like 0 to 120 miles an hour. Here we've got a very simple low voltage analog circuit that only works 5 or 10 volts. So we're going to have to take these values with a grain of salt, but it can help us at least get a conceptual understanding. All right. So this speed is going to be some value, and we're going to feed it into our brain, which is this differential amplifier, which takes the difference between the actual and the desired, or VREF, and comes out with an error signal. So now let's take a closer look at this error or differential amplifier. And again, this is a model of your brain riding your motorcycle, and coming in from the top is the feedback through the speedometer of what the actual speed, and here this voltage source is the reference or desired speed. So here we've got a simple op amp. I'm using an LM358. You can use a standard op amp, whatever you want, and I'm feeding it a VCC of 10 volts, and I've got the negative grounded. And this circuit right here is a very typical differential amplifier, and it takes the difference between this feedback voltage and this reference voltage and gives you an output proportional. And the proportional depends on these resistor values. In my case, I've got a gain of 10. I've got this feedback resistor and this positive to ground resistor of 10K, and the inputs are 1K, so the output is 10 times the difference of these two input voltages. Again, we can tweak those later on, but this is just some starting values. And the reference value that I'm using is a PWL file voltage, basically a step voltage that we saw here in the output. Basically, I'm applying a step voltage of the reference that goes up to 1 volt, and I'm using this PWL signal, piecewise linear. Again, we've got a video talking about how that works. But here is the text file which describes the PWL, piecewise linear signal. At time 0, it's 0 volts. At time 0.5, it's 0 volts. And right after 0.5, it goes up to 1 volt. And at 2 seconds, it's at 1 volt. So it's basically a step from 0 to 1 volt. And that basically gives us our V error, which is this voltage right here. Now what I'm doing in the circuit to get these output voltages looking kind of close to what we want, for example, you want the speed to look something like 60 miles an hour, is I'm taking the actual output voltage, whatever it is, and I'm multiplying it times 60 to give us something that looks reasonable. Again, we're working with a very low voltage system, so we're not going to get values that represent actual speeds or anything else. So keep in mind that these output voltages, I've basically gone into the expression editor and multiplied them times whatever works to make them look kind of reasonable. Example, this throttle value is going to go from 0 to 1. I had to divide by 8 to make this go from 0 to 1. Again, it's not really too relevant. It's just we're using it as a conceptual idea. So the output of your brain, or the error, gives us an error value that feeds into this proportional gain. And in this case, I'm just using a proportional gain of 2. Doesn't really matter. And I've got a 1K and a 1K, so the gain is 1 plus 1K over 1K, or 2. So I'm taking the error, multiplying it times 2 to get this throttle value. Again, we can spend a lot of time tweaking these to get more, to get different values, but in the end, not really important at this point. We just want to see the time response of this system as we give a step input in a desired voltage. So really, you can see we're basically just have our error detection. We figure out with a differential amplifier what's the error between the actual and the desired, and multiplying it times whatever value we want to get a proportional throttle position, and we're taking that output as a feedback. So here we've got a very, very simple model of a control system that we can put on the bench with just one op amp, a few resistors, and a capacitor, and a voltage source, and we're ready to go. As we mentioned before, for a real-world control system, we don't need to model this machine, right? We've got the machine. What we need to do is we need to model this control system on the left here that basically understands what the signal is going to be coming out of the machine as feedback, in this case for speed, and what we need as input for the throttle position. But otherwise, we can kind of erase this machine model and just focus on this control system model that will work with the feedback value and the throttle input and give us the correct control system. So now here is that circuit on the bench. You can see I've got on a little breadboard here, I've got my LM358, and I've got some resistors and a capacitor and a DC power. And I'm feeding it over here with my function generator. I'm feeding it a square wave. And here is the result. You can see in the light blue, you can imagine that is your hand on the throttle. And here we twist the throttle to maximum, and the speed of the motorcycle responds very slowly. And here we switch the throttle to minimum, and the motorcycle speed responds. So basically a very simplified version of a control system. And what we can do in the future is we can take this and start to modify it so that it works like an actual control system. And we can add to it some of the other functionality inside of a control system. So far, we've only showed what's called a proportional control, and there are other aspects of the control system to fine-tune it. So we can get into that if we get any views. Unfortunately, in the last 3 months, I've gotten like 170 views total on these videos. So I don't know, not a lot of encouragement to continue with this stuff, but such is life. Anyway, if you like any of these videos, hit the like button, subscribe, hit the bell notifications, and most of all, let others know that we're here so we get some views. Really appreciate it. Otherwise, take care. Have a really good day. Thanks.